Hello, in this video we introduce our system by which we can determine the cell potential between any two given half reactions. And so the system is called standard reduction voltages or standard reduction potentials, and from that we get cell potentials, E with a degree sign. Alright, so here's why. We want a way to compare half cells. What if I take this half reaction, put it together, make a battery? What voltage am I going to get? You could imagine that's a useful thing to know. And so how do we do this? Well, all that matters is the difference between these two half cells. It doesn't matter what anything else in the world is doing. So we can set one specific half cell as a 0, compare everything to that, and then if we want to find the difference between any two half cells, we can use these numbers. Very similar to other things we've done with Gibbs free energies of formation and enthalpies of formation. Same kind of idea. So in this case, our 0 we choose is the standard hydrogen electrode, which is 2H plus going to H2 gas. And the standard state is 1 molar and 1 bar. And this matters a lot. Just like Gibbs free energy, if we change the concentration or the pressure, then our E changes and this all goes to heck. So our tabulated values are all at standard states. And we set this particular one to 0. So this we talked about in the previous video, where you have hydrogen gas, HCl solution, and you have a platinum electrode. Or it could be any type of acid, as long as it's a strong acid. All right. So now, if you take any other given half cell, say the zinc one that we've been using, and hook it up to this standard hydrogen electrode, you'll get some voltage, okay. And this voltage will turn out to be the standard reduction potential of this zinc half cell. Okay, so the cell looks the same. We showed this in the previous video. Now we measure the voltage, and the reaction is the same as before, so that's not a surprise. Now, we set the standard reduction voltage of the H plus H2 gas half cell to be 0. So that means that the potential of this zinc 2 plus cell is 0.76 volts because the other one's set to 0. Now this technically is an oxidation potential. We compare reduction potentials, or reduction voltages, same thing. So we'll get to that in a minute. And then we also describe this whole cell as having a potential of 0.76 volts, because that's what we measured between them. And because one of them's 0, that means the other one is 0.76 volts. All right, so here's the cell diagram for this. We've showed this before in the previous video. Here's the oxidation, here's the reduction. And you add them together, you get the overall reaction. Again, we talked about this in the previous video, so I'm not going to belabor the point here. All right, so now looking at this cell, our standard voltage that we measured is 0.76 volts. And all right, so this cell potential comes from the reduction half cell potential and the oxidation half cell potential. And the reduction is H plus to H2. The oxidation is zinc to zinc 2 plus. Now we measure that as 0.76 volts. We set the standard hydrogen electrode as 0. So we can use this to solve for the oxidation potential of the zinc and zinc 2 plus system. And so that's specific for the oxidation half reaction at standard states, 1 molar. All right, so we can go with this. However, the convention is to compare reduction voltages or reduction potentials. And we have an oxidation one here. We need to convert it. So like Gibbs free energy for a reaction, when you reverse the reaction, it just changes the sign on the value. And so our half cell potential is just going to be the opposite sign because we can convert this oxidation into a reduction. So we'll list this as the reduction of zinc 2 plus going to zinc, and then switch the two things in here. So our reduction voltage for this is negative 0.76 volts. Now here's our value that we can list in the table. And so we do that. Here's a table from a different textbook. And the standard hydrogen electrode is right here, and we set it to 0. And then where'd the zinc go? Down here. And so the zinc is below that, negative 0.76, because zinc really doesn't want to be reduced, it wants to be oxidized. And we'll get to that in a minute. Your textbook, McQuarrie, has a much bigger list. Fine. And here's some things about it. So this standard potential is for the reaction as it's written over here. So if you reverse the reaction, you have to change the sign on the voltage here. And the more positive this number is, the greater the tendency for the substance to be reduced. It turns out when you wind up calculating cell voltages from the reduction voltage, a positive number is good. And so you'll get a positive number if you're higher up here on the list. And we saw that before. Zinc is down here lower on the list as negative because zinc really doesn't want to be reduced. It wants to be oxidized. All right. Now, these half-cell reactions are reversible. I just said that. Change the sign. That's great. Now, an odd thing is when you change the stoichiometric coefficients of a half-cell reaction, like if you multiplied this all by 2, you do not change the value of the reduction voltage. It's a little weird, but the way to think of this is that reduction voltages are intrinsic properties of the reaction, and so they don't depend on the amount of the reaction that's happening, and thus don't depend on the stoichiometric coefficients. And again, standard states were only valid for 1 molar. And so because the things higher up on this list are more likely to be reduced, that means if you put two half reactions together, whatever's on the top is going to still reduce, and whatever's below it is going to wind up being oxidized. And so we'll show this in an example here. So we have this standard cell again. Here's the oxidation states of all these pieces. Let me scoot this up. So let's figure out what the cell voltage is of this thing. And so first you look this up in the table. Here's the zinc, here's the copper. Now, as we said before, the copper's higher up on this list, so that means it's going to get what it wants. The copper will be reduced, and then the zinc will wind up being oxidized, which turns out to be what it wants also. So, okay, so we looked them up in the table. You got to figure out which one's oxidized and reduced. Right, here are the reactions for these things, which we also showed in the previous video. All right, that's all good. So we know the zinc is oxidized, the copper is reduced. Then how do we find the standard cell voltage for this, which is E naught cell? So the thing that's lower on the list, you flip it, right? And I'll show you why this works. So we have these two pieces that were in the standard reduction voltage table. And well, we're going to flip the one on the bottom. So now zinc is actually being oxidized, because up here it's written as a reduction reaction, but it is going to be oxidized in the end. So we reverse this, and then we make this sign plus 0.76 because we changed the sign. Now we still have the reduction reaction, 0.34 volts as its standard half cell potential. All right, and then you add these together, and then what you do when you add the reactions together is you also add the E naught for these reactions together. You add the standard voltages, either reduction or oxidation now that we've flipped this, and here we get a cell voltage of 1.1 volts. All right, so this is the whole point of this system, is that we can use these tabulated values in a way that would give us the cell potential, or the cell voltage, between any of these two reactions, half reactions. So we can generalize this process and say that E naught for the cell is whatever you have for the reduction plus whatever you have for the oxidation. And remember, we list reduction potentials in the table, so to find the oxidation one, you're going to have to reverse whatever reaction is lower on the list. Now another cool thing here is that the sign of the cell voltage gives you spontaneity. So if this number is positive, it's a spontaneous reaction in the way you have it written. And if it's negative, it's not spontaneous. Now remember, we're at 1 molar, and so this is just like Gibbs free energy, delta G naught. This tells us if you have 1 molar of everything, which way is it going to go? If you're at different concentrations, it'll be different, and we'll see that in subsequent videos. Now, if in the first semester of Gen Chem you learned activity series, and you had this kind of arbitrary list of metals and whatnot in order, this is kind of the basis for why that all works. It's because a spontaneous reaction is going to have a positive cell voltage, whether or not you separate them physically or not. If this is positive, it's going to go forward. All right, one last example. So the standard voltage for an electrochemical cell made of a cadmium electrode and a chromium electrode. And then they're both in 1 molar solutions of their ions. Cadmium's positive 2, chromium's positive 3. Why you would do electrochemistry with this? Cadmium is very toxic and chromium is pretty toxic? I don't know. But we can calculate it because we know how to do this, and it provides a way that we can learn something here. So this is what you'll find in the table of standard reduction voltages. So we can look at this. All right, who's going to get reduced? Who's going to be oxidized? Well, remember, the one that's highest up in the table, so that's the largest, E naught, is reduced. The way I think of it is it's a pecking order. If you're higher in the table, you don't have to change because that's what you want. If you're lower in the table, too bad, you flippin'. So we're going to do this. So we're going to keep the cadmium as the cathode, the reduction, because it's higher in the list. And then we'll flip the anode. And so that would be the chromium. Now it's 3 plus, solid. Okay, so this is reversed. When we do that, we change the sign on this. Now, do note there's different number of electrons here. And so if you're going to write the balanced reaction, which sometimes we ask you to do, just we want to see if you know how to do that, you have to multiply each of these by 2 or 3 to get to their lowest common multiple. And so this is your overall balanced reaction. This is just from the how do you balance redox reactions thing in some previous videos. But when we do this, you don't multiply the half cells by 2 or 3, because remember, it's an intrinsic property. It doesn't matter how much there is. This is different from other things we've done, like Gibbs free energy and enthalpy. That matter. It depends on how much there is. But potentials or voltages don't depend on how much. Current depends on how much, but not the potential or the voltage. Okay, so when we plug these numbers in, we basically just add them together, and then we see that for this electrochemical cell, that the overall cell voltage is 0.34 volts. Great, so this is a spontaneous reaction, and you can go from there. Now, when you're doing this like the way we've just done it, pulling things out of the list, you're always going to make a spontaneous reaction, and that is why you reverse the one that's lower on the list, because it gives you a positive number if you do that. If you were to flip the top one and not the bottom one, you'd get a negative number, and that's not a spontaneous reaction. So we're always going to mess this around in order to make this positive when you're just, calculating cell voltages on some given set of half cells. All right, last thing I want to say in this video, please excuse me that I switch back and forth from potential and voltage. They are the exact same thing. I learned how to do this all with potential, and then your textbook uses voltage. Oh my gosh. So I'm trying to say voltage, but it's a bad habit I can't break. They're the same thing, so it's good to know both, for sure. All right, thanks for watching.